who was an undergraduate at Cornell University in in chemical engineering. She did her doctoral work here under Per Peterson. Before her doctoral studies, she worked at GE and ExxonMobil. In 2011, she advised Hitachi GE in Japan on post-Fukushima changes to severe accident guidelines for the Japanese fleet of reactors. In her current work, she studies thermal hydraulics, chemistry, and mass transport in molten fluoride salts. She works in heat and mass transport, thermal hydraulics, nuclear reactor safety, design, and engineering ethics. I had the privilege in 2013, we were both Minner Fellows, the Warren and Marjorie Minner Foundation, which gave a large grant to the university to sort of instate engineering ethics into the curriculum here. And so we spent a week together with Professor Junhong Han, Bill Kastenberg, and other experts in engineering ethics here as well. She has a great commitment to engineering ethics, has created curricula and so forth. Without further ado, the title of her colloquium today will be In-Core Tritium Uptake by Graphite in the Fluoride-Salt-Cooled High-Temperature Reactor, FHR.
Thank you very much for the introduction, and thank you everybody for being here and for coming here on a Friday afternoon. I have to say it's extremely exciting to give this talk here because with this talk I try to bring in a little bit more of the chemical engineering and the chemistry into the nuclear engineering work that I do, and with the department having been founded by Thomas Pickford from chemical engineering, it's quite an honor to give this talk here. So the work that I do, I say chemistry and chemical engineering. Chemistry has to do with understanding the fundamental chemical forms of species and various solvents in media, and then chemical engineering has to do with understanding how those species transport. And so I bring a little bit of those two to nuclear engineering, and those types of questions are important in severe accident analysis if we want to know how radioisotopes transport in the environment. They're important in repository performance if we want to know how radioisotopes transport in the environment. They're important also in reactor design and safety analysis if we want to understand how radioisotopes transport within the reactor. And so those are the types of questions that I work on, and today I'll talk about one of those questions, which has to do with tritium, the tritium isotope. And specifically with tritium in molten fluoride salt media. Molten salt media are used for separation, so pyroprocessing, and they've also been proposed as coolant for fusion and fission reactors. And so to give you an idea of the type of materials that we work with in my group, I don't know, is it possible to turn down the lights just a little bit just for a second? And so what you see here are two droplets of salt that are melting on a nuclear graphite surface. This is flibe, this is flibe, and you can see that this salt is recirculating. And what's remarkable about this is that this is a 4 millimeter droplet. The movie is sped up about 8 times, so it's a little faster than real time. And the temperature gradient is probably very small. What's happening here is that the surface of the droplet is radiating out to a colder lid, and the bottom of the droplet is hot, and that very small thermal gradient is creating a recirculation within the pebble. What's also remarkable is that you see this skin that's forming, and that's the frozen liquid that's melting and freezing and melting and freezing. And so these are some of the problems that I study. How do isotopes transport between phases, between liquids and solids, and between gases and liquids and solids as well? It's harder to see, but there are bubbles in there as well circulating. So we'd like to know how isotopes transport. And also what's remarkable is that these droplets that you see are at 460 degrees Celsius, and they're at atmospheric pressure. And so we can do high temperature separations and high temperature reactors at atmospheric pressure, which has an inherent safety advantage. So some of you might remember this cover page from the New Yorker. This was in March 2011 after the Fukushima. Systems that employ high temperature coolants that remain single phase and don't build up pressure have an inherent safety advantage in that you're removing one of the risks, and that source of risk is stored mechanical force that can disperse radionuclides. So that's one of the motivation of studying these kinds of liquids is that they have inherent safety features and passive safety features. Now another motivation is that we really need clean sources of energy quickly, and we need to make sure that the new sources of energy that we come up with are clean and sustainable. And so we have to figure out the safety analysis of the reactors as well as the entire fuel cycle, and to make sure that we're not making a bigger mistake than we've already made with other sources of energy. So that is the background and the motivation of the work that I do. And so now I'll tell you about one of the problems that I tackle, which is tritium transport in a specific system, namely reactors that are cooled with molten salts and that have solid fuel. So here is a picture of matrix graphite pebbles that float in a flibe salt that demonstrate the concept of salt-cooled reactors. You have graphitic fuel that floats on a Fluoride-Salt-Cooled. Now there are a few differences here than what you would see in a reactor. One is that this picture was the first picture that I took in my laboratory about two and a half years ago when we were just starting up. And this was the easiest thing we could possibly do. Take a Bunsen burner, take a test tube, put some salt, put some hand-polished graphite pebbles, and see what they look like. And so it's in air. So that's the fact that it's in air. Obviously, it's not blowing up or exploding or combusting, so that's good. This fluid is inert in air. However, it is changing chemistry slowly, and so you can see that there's some sedimentation here that comes from the fact that you're beginning to form oxides from air exposure. And so that's going to begin to change the chemistry and the way radioisotopes partition within your fluid. And so most of the work that we do is in an argon atmosphere, in an inert atmosphere. And then this is a cross-section of what a fuel element would look like. You would have triso particle-encapsulated fuel that retains a fission product within the particle, and these particles are embedded within a graphite matrix. And so I highlight the graphite matrix because what we study is the transport of tritium from the salt into this graphite matrix. Now, I mentioned chemical engineering. Well, chemical engineers and chemists like phase diagrams. So I had to put up a phase diagram of the coolant because the coolant is not just a coolant, it's actually a mixture of salts. And in this case, it's a mixture of lithium fluoride and beryllium fluoride. And we operate somewhere here, so somewhere here, and so somewhere there. That's a zoom out. But we're not always quite on point. This is the spread of compositions that the molten salt reactor experiment in the 60s had prepared for their reactor. So every batch was a little bit different, and as you run it, the composition might also shift for several reasons. So it's important to keep that in mind, that composition of the coolant will evolve in its chemistry, and it can vary in its chemistry, and that will affect the thermophysical properties and the transport properties. So here, for example, you see the plot of viscosity which changes in composition, and then viscosity is important for thermohydraulics, and then density might change as well, and density is important for neutronics. And so we need to keep in mind that in addition to in addition to temperature, we also have a few other axes of composition. So that being said, if you take this coolant and this solid fuel and put them together, this is what a reactor design might look like. You actually start the design from the turbine and then design a reactor to fit the turbine. And there's so many of you here that have been part of generating that design that I will just say that this enables us to produce peak power with nuclear energy, and which puts nuclear energy in a different market, which then gives it maybe a bigger chance of competing with fossil fuel and displacing fossil fuel as a source of energy. And so that's a good reason to work on this technology, to try to make it work. And then this is applicable to fission systems. It's also applicable to fusion systems that might use the same coolant for tritium breeding and also for heat removal. And so the fact that these coolants remain single phase up to high temperature, it enables them to run gas turbines, which can then do power peaking by gas co-firing. So this is the system that we have. Here's a core. The salt flows in, down, up, out, and over to a salt-to-air heat exchanger. This is a pebble bed with fuel, and so the salt flows through the pebble bed. As the salt is irradiated by neutrons, it produces tritium, and then tritium travels to the salt-to-air heat exchangers, and the tritium production in coolants is not unique. All reactors produce some amount of tritium of some sort. But what is unique is that we're at high temperatures, and at high temperatures, metallic components are transparent to tritium. So since we have a salt-to-air heat exchanger, we transport the tritium will leak into the air, which will then reach the turbine and be sent up the stack. Since this is an open-air Brayton cycle, you send all the tritium up the stack that goes into your turbine. And so we need a sink for tritium. And so maybe that sink will be the fuel elements themselves. And that would be a good sink to have, because the fuel elements are removable. And so you have a renewable tritium sink. They have a high surface area by design because they need to remove heat from the fuel. And so mass transport will also be advantageous in that sense. And then they're graphite, and we know that graphite has some affinity for tritium. And so then we set off to answer this question: can we use the fuel element as a sink of tritium from the fluoride salts? So that's the question that we will talk about for the next half an hour. And there are three components here. There's tritium, there's salt, and there's graphite. And so we haven't yet run any experiments with the three of them together, but we've run experiments 2 by 2. So I will show you the 2 by 2 experiments. And then at the end, I'll tell you how we hope to bring everything together into a joint experiment. So we'll talk about flibe and tritium. Flibe is the coolant of interest here, lithium fluoride, beryllium fluoride. We'll talk about graphite and tritium. Then we'll talk about flibe and graphite. So this is not a picture of flibe, it's a picture of potassium fluoride, zirconium fluoride. This is work that's sponsored by Terrestrial Energy. They're interested in thermophysical properties of these salts. And coincidentally, we managed to make a lot of bubbles in this salt. It wasn't our intention, but we did. And I thought that just conceptually, it represents the idea of we're producing tritium in the salt. And tritium may be solvated, but it may also be in the form of bubbles. And so that's just the concept that I am imparting to you for the next set of slides. Is we're going to talk about the tritium that's produced in the salt. So how is tritium produced in flibe? The main activation pathway is from lithium-6. You have N-alpha to tritium. The constituents of flibe are lithium, fluoride and beryllium fluoride. And you might notice that it's isotopically rich in lithium-7, and that's because lithium-6 is a breeder of tritium. And so if you're a fusion system, you're going to enrich in lithium-6 so that you produce much more tritium. If you're a fission system, then you're enrich in lithium-7 so that you need a smaller sink for your tritium. However, we also have beryllium. So we also have beryllium as a constituent of the salt, and the natural composition of beryllium is 100% beryllium-9. Beryllium-9 will, by N-alpha, will produce helium-6, which decays to lithium-6, and so you're continuously producing lithium-6 from beryllium-9. And beryllium-9 is 100% beryllium-9, and so there's nothing we can do about that. We can isotopically enrich lithium in lithium-7, but we can't do much about beryllium. And so what happens is you'll enrich the lithium-7 as much as you can. There it's an economic balance. The more you enrich it, the less of a tritium problem you have at the beginning. And then you'll burn out your lithium-6 up to some steady state composition that balances the consumption with the production from beryllium. And so the tritium production rate in an FHR would look something like this. In this case, it levels out in about 2 years of full power operation. And FHR stands for Fluoride-Salt-Cooled high temperature reactors. So it's the concept that I showed before. But it's similarly in fusion systems. If you're not replenishing your blanket in lithium-6, then you might see the tritium production rate drop off. Okay, and then another thing to notice is that at the steady state lithium-6 concentration, you get about 40% tritium production from lithium-7, and then 60% from lithium-6. So lithium-7 also produces tritium. Where is lithium-7? It produces...
Yeah, and then private alpha.
And then alpha.
Yeah.
You get your nickel back with lithium-7, and then you have another reaction with lithium-6.
Oh yeah, okay.
It's endothermic.
It's endothermic?
Yeah.
Okay. And so those are the two major contributors to tritium production. Now another thing to note is that there are other activation products in the salt from fluorine. So you can produce oxygen and nitrogen. And fluorine-20 is important because it decays to neon, which then gives off an energetic gamma, and the same with nitrogen-16. But the fact that you're producing an inventory of new types of anions, so instead of fluorine, now you also have oxygen and nitrogen and possibly carbon further down the line, that's going to change your chemistry. And so it's important that we run the numbers for this so we know how much the chemistry evolves. And then to put into context, the tritium production rates, they're about 200 gram per year per gigawatt electric. And this is assuming the steady state lithium concentration and 60% power conversion efficiency. Since I'm dividing by gigawatt electric, it's important to know the assumptions. So that would be that would sustain about 10 megawatt electric of DT fusion. So in the fusion world, this is not a lot of tritium. However, if you compare it to PWR production, which is about 2 grams, it's a lot of tritium. If you compare it to BWR production, which is about a fraction of a milligram. Again, it's a lot of tritium. CANDU is comparable, same order of magnitude. And high temperature gas cooled reactors produce tritium from the helium-3 in the coolant as well as from the lithium impurities in their graphite fuel. And so really any kind of system they can think of will produce tritium in some amount. Another point of reference to keep in mind is what is released. And so for PWR, there are liquid effluents that are released. The Tritium comes from the lithium and the boron. Lithium is used for chemistry control in PWRs. Boron is used for chemical shim, and so that produces tritium. And since it's a water system with valves and pumps and systems that leak in some amount, eventually you end up with some liquid effluents that are released to the environment. And so it's a fraction of a gram per year per gigawatt electric for PWRs. And then for BWRs, I found it interesting that on the NRC website there's some 2003 data of releases in the milligrams, but the production rate is estimated as 0.01 milligrams, so they must have somehow stockpiled in 2003 and accidentally released it. I don't know what the story is there. And then, let's see, other interesting points of reference. If we were to release all of the tritium out the stack through the air turbine, that provides a dilution stream, just the gas that runs through the turbine. And that dilution would bring it down to 10 microcurie per kilogram of air. The NRC emission limit is 0.05 microcurie per kilogram of air, so we're not diluted enough. We definitely need to do something about the tritium. But regardless, we wouldn't want to send the tritium up the stack even if we had diluted it well enough. And then also it's interesting to note that there is natural production of tritium from cosmic radiation. And it's about 25 gram of tritium per year, so in 1 gigawatt of FHR we produce 4 times that. Okay, so that gives us the context for how much tritium it is that we're producing. And it's produced in the core, and we would like for it to be removed before it leaks out of the heat exchanger to the airstream. And in addition to having a sink in the system, it's also important to work on tritium permeation barrier on the heat exchangers. That's not going to keep the tritium in, but what it does is it allows you to tolerate a higher concentration of tritium in your primary coolant. And so if you have a higher concentration of tritium in your primary coolant, the residence time of tritium in your primary coolant is longer. And if your residence time of tritium is longer than the residence time of the liquid going around, then that means that you can use a fraction of your stream for your purification system. So for example, if the tritium production rate is 95 grams of tritium per year, the concentration, let's say, is 10 to the negative 4 gram per meter cube, and then the total inventory is about 0.05 grams of tritium in the total primary system. We know the tritium production rates, and that gives us 4 hours of residence time for tritium in the core. We can run the same number on the coolant going around the core. If it runs at 2 meter cube per second, and the total salt inventory is 100 meter cube, then the salt residence time is about a minute. That's actually remarkable, that it takes a minute in full power operation for the coolant to go all the way around the system. This means that in decay heat levels, you're at a half an hour of the coolant traveling around until it makes it back to the core. That's a really slowly evolving system. So that's nice for safety, so operators have time to make decisions. But sorry, that's an aside. We leave that aside alone. We come back to tritium. So longer tritium residence time means that you can use just a small side stream to purify, to remove the tritium from the core, and so that's convenient. Now another thing that a higher concentration of tritium in the coolant does is it gives you a larger term for the mass transport. So if you want to transport tritium from the bulk of the salt to the surface of your fuel elements, there's a mass transport resistance there, and the higher the concentration gradient, the easier it is to remove. So let's look at the mass transport problem. And I know it's a very busy slide, but bear with me. It was important that I put everything in one picture. Okay, so I'll walk you through it. So what you see here is this bulk salt and the salt surface. So here you have the salt-graphite interface. That's the graphite surface, and that's the salt surface. And then you have the graphite bulk, and then you have the gas phase. So if you assume that you have 0 concentration at the salt surface, and you know the flux that needs to go into your fuel pebble, then you can, and you know the diffusion coefficient and the mass transfer coefficient, then you can calculate what the concentration of tritium needs to be in the bulk. Now what's interesting about tritium is that tritium can take many chemical forms. It could be a molecule, it could be an ion, it could be an atom, it could be an anion, but we won't talk about anions. So to simplify problems here, we're just going to talk about molecules and cations. So it can be T plus or T2, let's say. And T2 won't have a very high diffusion coefficient in the salt. T plus will be the one that will diffuse quickly. And so if you compare the diffusion coefficient of T plus, for example, with the self-diffusion coefficient of F minus, you'll see that they're sort of comparable. And so that's an indication that it's probably T plus that's diffusing through your salt, not T2. And so what you need is this concentration, 10 to the negative 6, to drive the mass flux in. And then you know that T plus is in thermodynamic equilibrium with T2. And so that thermodynamic equilibrium is set by how you do the chemistry control in your system so that you don't corrode your metallic alloys. So just like T2 can be in a 0 oxidation state, so it's T2 covalent, they share electrons, or in a +1 oxidation state, it's missing an electron. Same thing with metals. You can have chromium 2 plus or chromium 0. We like to keep chromium in a 0 state. So we like to keep it in our pipes, in our structural materials. If it goes into a 2 plus state, then it dissolves in the salt, and so we're corroding it. So you're going to set your chemistry control system so that it's somewhere towards the 0 oxidation state. And it's going to have an effect on tritium as well. So it's going to be pushed towards here. And so if you need this T plus concentration to drive the mass flux, it means that you need this T2 concentration that's in equilibrium with this T plus concentration. So then from there, each of these species has a partial pressure above it, above the salt in the gas phase. And so we can calculate what that is. For T plus, it's 0.01 Pascal of TF. And then for T2 is kind of high. It's 180 Pascal T2. It's higher than I would have expected. I think that's going to be a pretty good driving term for leakage through the heat exchanger. It's lower than any data that we have. So that means that we need data at low partial pressure. Most data is at 1,000 Pascal and up. So that's where, and then you can go and calculate the tritium inventory, and that's where those numbers came from that I showed you before. But the main takeaway here is that tritium transport is tightly coupled to chemistry control, which is tightly coupled to corrosion. And T2 is the one that diffuses through the metallic components. T plus does not diffuse through metallic components. And so if you're controlling your chemistry to be more towards this side, that means that you're going to have a higher driving term for leakage out the heat exchanger. So maybe we can play with the chemistry. So it's different in the heat exchanger and it's in the core. I don't know. But it's a degree of freedom that we have to consider. All right, so that was the first part, the flibe tritium. We talked about tritium production, other activation products, the tritium concentration in the salt, and then the speciation, which is really important. The next topic is graphite tritium. And so what you see here are 2 types of graphite. This is nuclear grade graphite, this is matrix graphite. This is what's in the fuel, the removable fuel elements. This is what's in the reflector blocks, and also possibly in some of the pebbles, because you have a pebble bed. And you could put fuel, but you could also put pebbles of other materials. And most of the data that exists in the literature is from nuclear grade graphite. Matrix graphite hasn't been well characterized, primarily because it's scarce. Not a lot of people manufacture it. So we're very grateful to Oak Ridge. Tim Burchell's group at Oak Ridge National Lab has provided us with matrix graphite, and so we're very grateful to them for that. And what we're trying to understand here is what is the difference between these two materials, so that we know if the knowledge that we have from IG-110 is translatable to the, from the knowledge that we have from nuclear graphite is translatable to the matrix graphite. So the first thing we did is there was one data set from the molten salt reactor experiment where they took a graphite stringer, a long graphite column that had been immersed in the salt for 1.5 years during reactor operation, and it had taken up tritium, and they took slices of it and quantified the tritium profile with that. And so we wanted to know if we could match their data with a diffusion model based on diffusion parameters for hydrogen in nuclear grade graphite. And the answer is no, we cannot, because the shape that that profile has just does not fit the shape of a diffusion profile. What you have is a very flat gradient in the center and a very sharp gradient at the surface. So there are two choices. Either the graphite is not homogeneous, so somehow its diffusion coefficient is different in the outer 0.2 millimeters, 0.5 millimeter, or there's a different mechanism of transport that's happening. And it's possible that it's both. We're very grateful again to Oak Ridge. They gave us one of their graphite columns to characterize. Fred Perez and Dave Holcomb helped make that happen. They have the molten salt reactor experiment has never been decommissioned, which I think is a huge failure in demonstrating that technology. All of you out there who are going to go start reactor companies, make sure you design them for decommissioning. So it's never been decommissioned. It's sort of sitting there with the fuel in the pod, and with the salt in the pod, and they can't open it. And then they have people that just watch it mostly. So we took a tour, and then there's this warehouse. So we said, "What's in the warehouse?" And they said, "I don't know, dusty stuff." And, then there was a whole pile of graphite stringers. So it was Christmas. Oh, can we please have one of these? So they said, "Well, I guess." So they worked really hard with all the Oak Ridge bureaucracy, and they sent us one, and we were very happy. So now we're analyzing it to see if it is indeed a porosity gradient from the surface to the bulk, and it seems to be the opposite. It's more dense at the surface, and the graphite experts tell me that it has to do with how they impregnate it to increase the density, and so it's probably not the lower density at the surface that is explaining that, but we're still doing that study, so don't take my word for it yet. But there's another reason that that profile might look different, which is that when graphite transports, when hydrogen and tritium transports within graphite, it bonds chemically to the graphite. Right. And so what you have is not just a diffusion process, but you have a trapping and detrapping process. And so then we have to talk a little bit about the structure of graphite. Graphite is, you can think of it as a composite. It has grains of about 20 microns. And the numbers that you see here are numbers that we have from the characterization that, the microstructural characterization that we did on those two materials that I showed you. And so the nuclear graphite has grains of 20 microns, the matrix graphite has grains of 10 microns. And then within those grains, we have what we call crystallites. And crystallites are graphene sheets stacked on top of each other. And these crystallites are on the order of 20 to 30 nanometers in diameter and height. And at the surface of these crystallites, at the edge of the graphene sheets, you have dangling carbon bonds that aren't satisfied, it's not bonded to other elements. And so that's a place where tritium can trap and can chemically bond. And so the main question is, what is this trapping site density in the graphites that we work with, and then what is the transport resistance to get to the surface of these crystallites? Okay. So then one way to study the behavior of these, one way that the behavior of these traps has been studied is with thermal desorption analysis. And so a graphite that's been exposed at 700 degrees Celsius has desorption peaks at various temperatures which correspond to different types of trapping sites that have different energies. So we care about that because we want to have a chemical transport model for hydrogen moving into the graphite so that we can match that profile that we saw in the MSRE. Another thing to keep in mind is that the diffusion coefficient and the trapping site density evolves with irradiation. And so doing measurements on non-irradiated graphite is probably very incomplete in terms of having the full picture of the lifetime of each fuel element. And so what's important, however, is to understand mechanistically what are really the microstructural parameters that you care about for the graphite in order to then predict the trapping site density and the diffusion coefficient. And then so that's the mechanistic side, and then at the same time you need to push the engineering too and just irradiate some graphite and measure how much and how fast it absorbs. Now what's important is how fast is also important. So we can't treat the graphite as a point absorber. The time of absorption into the graphite is also important. So here's an example of non-irradiated graphite exposed to hydrogen for 1 minute and then for 100 days. And so you can see that the hydrogen uptake goes up by an order of magnitude in that time. And so the time it takes for a graphite sample to load with hydrogen is on the order of days, tens of days, hundreds of days. So if you have a graphite pebble traveling through the core, we can't assume that it instantaneously sucks up the tritium, that it instantaneously gets to thermodynamic equilibrium. We need to understand the time evolution as well. And then that time evolution evolves with changes with irradiation. So that's non-irradiated, that's irradiated. Okay. And so then what microstructural characterization of these materials enables us to do is to predict things like trapping site density. And so here is some data for trapping site density versus the lattice constants of those graphite crystallites, and then this is where we fall for the materials that we've characterized. So a few takeaways is that hydrogen chemisorps, the timescale matters, and the irradiation effects are important. And then lastly, flibe and graphite will be a very quick conversation because I have 10 minutes left. So we want to understand if we were to take the hydrogen graphite data and the hydrogen salt data and put them together, would we get the right number for hydrogen from salt into graphite, or is there some sort of interface reaction that happens between the salt and the graphite that changes the tritium transport? And so we exposed nuclear graphite to flibe for 12 hours at 700 Celsius, and we observed these intriguing spheres. And we want to know what they are. Mass spec shows us that we have beryllium, lithium, and fluorine down to at least 5 microns. And okay, something's happening, something's going in. But what we just learned yesterday is that, this is data from yesterday, the metal to fluorine ratio is 100. So we either have metals or chybarides or hydrides, but we don't have fluorides, which is, yes, I agree with the reaction. So, fascinating. So these are some of the things that might be happening. There's some data on the fact that lithium carbide is thermodynamically favored at 400 Celsius. To keep in mind is that lithium is liquid at 180, so we might be forming liquid droplets of lithium that then freeze? I don't know. It's puzzling. I just got this data yesterday, so I apologize if the analysis is not complete, but it's puzzling. And we should figure out what's happening. Because it would definitely affect tritium absorption. If you have metal, then tritium will form hydrides, so that's going to be different than tritium forming chemical bonds on graphite. So we need to figure that out. Now, another thing we learned from XPS analysis of the graphite is that the graphite fluoridates. So the sp3 carbons go from 10% to 5%, and then they show up as fluorinated graphite. So we fluorinate the graphite. Not much, but a little bit. And then that's also corroborated by the F-peak on XPS, which shows the same functional forms as we saw in the carbon peak. So graphite fluorinates. Okay, so putting all of those together, we still have some fundamental questions about like tritium, about the speciation in the molten salt and how that affects the transport path. We still have some important questions about hydrogen and graphite and how irradiation affects tritium uptake in graphite. And then we definitely have some interesting puzzles around flibe and graphite. And so in order to do all of this work, I'm very grateful to DOE and NRC for their funding so we can set up our labs. And also to the students who worked very hard to set up glove boxes. This is one of the glove boxes that we work in, and this is what work looks like. It takes about a day to prepare one melt, which in my opinion is excruciatingly slow, and we need to find better ways to do that kind of work, but that's the state of the art. Any experiment takes at least a week. Then we work with beryllium, and so we take beryllium safety very seriously. We do, so all of the beryllium that we work with is contained in glove boxes, and our labs are not beryllium contaminated, but we do monitor the labs for beryllium contamination, and anytime we do cleaning, we suit up just in case there's hotspots of beryllium that we haven't detected. So we do periodic house cleaning where we suit up and we scrub the floors. And then anytime we open the glove box or do any retrofits to the glove box, then we suit up. So we do surface wipes and air monitoring. And we aim for 0.2 microgram per centimeter square for surface swipes, which is the DOE recommended action limit. And so the interesting fun fact here, aluminum plants use fluorides as a solvent for electroweaning of aluminum. It's a similar process as you would use for pyroprocessing spent fuel. And the aluminum ore has beryllium as one of its constituents, and so it accumulates in the pot, in the electrochemical pot, and it's a beryllium exposure hazard for the workers because it's an open pit that they sometimes do maintenance on. And so there's some data from the aluminum industry on how to monitor and what the background levels are. And I will say that compared to other metals, the tools both for health monitoring and for detecting beryllium are not as developed as they are for things like mercury or other toxic hazardous metals. And we could definitely improve them. I don't think it's because we can't do it. I just think there aren't enough industries working in this area. So that's an area to improve. And this is a picture of our group. That's a piece of the graphite stringer. This is Gregory Ferschbau, who's a professor in photography, and I'm very grateful to him for a lot of the images that you've seen in this video. And then these are graduates and undergraduate students that work in my lab. And so, so I talked to you about tritium transport, but there are many other questions related to transports within the salt media that are still to be answered. In order to answer those questions about thermophysical properties, about transport properties, we need a more fundamental understanding of the melts, the structures in the melts, and the speciation in the melts of really the entire periodic table. And in order to do that, we need better tools. And so we've been working on electrochemistry and optical spectroscopy. It seems like yes, of course. If any of you work in aqueous chemistry, of course. What do you mean you've been working on electrochemistry? Well, these tools aren't established for molten fluoride salts data because of the material compatibility issues, because of the experimental challenges with these kinds of materials. And so we're working on establishing them so that we can do more fundamental studies. And then all of the chemistry and mass transport also ties into thermal hydraulics because we need to know the velocity and the thermal fields. And so we're also doing model development and experimentation in thermal hydraulics. And so hopefully all of this research will then lead to a more thorough understanding of the entire periodic table dissolved in the salt. That's important again for separations. It's important if you're going to run a liquid fuel reactor so that you know what precipitates out and what goes up in gaseous form. It's important for solid fuel reactors so that you know if your fuel leaks, then where your radioisotopes end up. And also if there's a severe accident, you want to understand what the transport paths are to the environment. So this is a marked up. This is to show that everything is so very much in progress and not well understood. So it's all sketched up and overlapped. That's how I see the field of this field. There are a lot of very interesting questions. And so because this field is so big and there's so many interesting questions, another thing that we really need is high throughput experimentation so that it doesn't take a week or a day to do one sample point, so that you can have a grid of maybe droplets 10 by 10 that you put on a grid of printed electrodes, and then you investigate optically from the top, and then you can scan the entire composition range. And so we've been doing some thinking around how do we do high throughput experimentation on high temperature liquids. And I will leave you with a video which originated from us wanting to measure the contact angle of the salt, and we were doing this work with the photography professor again, Gregory Hirschbaum, and he said, "Oh, can I have some fun now? Can we freeze them and see what they look like, and I'll take a video?" And so, so we said, "Yeah, sure, we'll have some fun." And so this is what we saw. This is flibe again. It's circulating furiously here. This is 8 times sped up video, and then this is flynac, and you'll see it starts to freeze from the top, and then you have these crystals that drop, and then it freezes from the bottom. And then you'll see flibe begins to freeze from the bottom quite differently. So there we go. And so this, of course, has implications in terms of both thermal hydraulics and mass transport, and it helps us with the high throughput experimentation as well. So with that, I'll take any questions.
I have 2 questions. One is about methane and acetylene production, because Olander studied that, to some extent. In your temperature range, that was the primary process he saw.
Okay.
It was the transport of the tritium off in the form of tritiated methane and tritiated acetylene.
Okay.
And the other question is sievert.
Okay.
A lot of these tritium permeation follow Sievert's law, where the throughput goes like the square root of pressure, not like the pressure, because the atoms have to go single file through some lattice.
Yes, yeah.
So do you have any Sievert coefficients to worry about in this work, or are you all in such a high pressure regime that it's all fixed law?
No, we do. Actually, in the melt, so I simplified a bit the problem when I said that there's T2 that's solvated.
Yeah.
It's quite possible that you have complex ionic structures that form in the melt, and those coordinate individual tritium atoms, and so in that case the solvation is done by dissociation and solvation of atoms. Mm-hmm. So in that case your dependence is to the square root of 2. As some of the students learned today, that square root of 2 comes from the 0.5 coefficient in front of the T2 goes to 0.5 T salt. So I see some of you laughing. Anyway.
Oh, and another point for historical record, if you didn't think lithium-7 was important, you should read about Castle Bravo. That was a nuclear shot we did in the Pacific, and it had 3 times the yield that we calculated because they forgot about the lithium-7.
Okay, I'll look that up. Yes.
Thank you for your presentation. Appreciate that. Based upon my past experience in the liquid metal world, something you might think about when you go to combine, you have the pairs, right? And now your next step is going to be to put all 3 together, right?
Yeah,
You know?
yeah.
So something that seems to happen in the liquid metal world when you're talking about oxidizing, where the liquid metal would be like your molten salt, and you have your substrate steel, which would be like your graphite, and then you have a gas, in our case oxygen, in your case tritium or hydrogen. That it's like the liquid metal accelerates the reaction between the gas and what's oxidizing. Because it isn't in the diatomic form. It's in the well, in our case, atomic form, or in your case, in ionic form. So you might anticipate that there would be some change in your kinetics when that happens. And I wonder if you could investigate that with hydrogen first, so as to avoid the tritium aspect of it, and see if you're going to anticipate an effect. But
Yeah, absolutely. It would be really interesting if we can probe that spectroscopically, if we can see if hydrogen really does coordinate onto those complex ions. It would be challenging, but something we can try.
In these contact angle measurements, I was wondering, when you see this solid forming on the surface because it's colder, wouldn't that mess with the data at the end? Was this still a valid measurement? Because the earlier one you showed that, wouldn't you have to heat the surface of those droplets? With
Yes. So for the contact angle, we want the droplets to be isothermal. For the sake of entertainment, I
I
wanted
see.
to
So
show you
it's,
the
okay,
picture.
all right.
But
But you have a heating lamp, right? So
it's an
Also-
oven that would be.
because
an
you said you're
isothermal.
heating the graphite bottom part, right? But then the top would still be cold.
Yeah, so depending on how we set it up, the idea is that we would have it isothermal with the top also heated and with a window on the side. In that case, it was being cooled so that it freezes, or so it had this recirculation path. But the goal is to have everything isothermal with a window on the side.
Right. So, okay.
But that is still useful in that we can see the volume shrinkage. So you can, as the droplet cools, you can see that it shrinks in volume. So the freezing, the solidification actually has other uses as well. I'll show you. I guess I turned up. So we would like to use now these droplets for solidification studies in and of themselves. Because we know that flibe supercools quite a bit, about 40 degrees we've seen. And so we want to study that visibly, optically as well.
But the supercooling, wouldn't that depend if you have nucleation sites or not and how clean it is?
It does, yeah. So, but we have the graphite environment that's polished, and so. Yeah.
So how does it make a difference if it's nuclear graphite or not nuclear graphite?
Yeah, let me actually.
What is actually the difference? In fact, how do you make the difference?
Yeah, so they're made differently. The raw material is different. The pitch tar is the raw material for nuclear grade graphite, and then it's carbonized to high temperatures, 2000 or so. The matrix graphite uses natural flake graphite as one of its main raw ingredient, and so that natural flake, and as well as a little bit of synthetic graphite and a resin, and then that's baked at high pressure at 700 Celsius, and then baked at not high pressure to 1200 Celsius. And they can't go high enough because then they would damage the triso particles. So that matrix, that filler material is not fully graphitized, but the natural flake graphite is more graphitized than the nuclear graphite. And so you end up, basically matrix graphite is a composite, whereas nuclear graphite is more of a graphite.
And how would that affect the?
Yeah, so let me show you.
You also saw that the crystal size was different, if I remember right?
Yeah, so basically the crystallite size, just a second. Is that back up? Oh no. Is at the end of the projector?
You have to hit the on button.
Okay, so I'll make the answer shorter. The distribution on the IG-110 is broader in terms of crystallite size. So it's hard to tell which one would be better. They kind of fall in the same range, but one is less homogeneous than another. So the crystallite size affects the trapping site density, but it's a little harder to. We're comparing apples to oranges because the matrix graphite is not just the crystallites, but this composite, and we don't know how that semi-graphitized material traps hydrogen. So we can compare the crystals in the A3 with the nuclear graphite. That we can do, but we can't compare the semi-graphitized binder to the nuclear graphite because we don't know how to do that yet.
And from a mental perspective, wouldn't it be interesting to study the hydrogen, tritium, through a highly oriented graphite, where you have pure just graphene layers, just really understand the diffusion process, the trapping, and not deal with all this other stuff which is in that graphite?
Yeah, we should start to work with the model system. That's a good idea. We've been doing something around that. Actually, we want to work with fluorinated graphite and fluorinated graphene to see if it behaves like the salt, like the graphite that's been exposed to the salt, where we saw fluorination. So another way to verify that we've seen fluorination. So yeah, working with model system is definitely a good idea, and we've been doing some thinking around that.
Just one quick question. Imagine we have the real reactor and it's running. The one that someday will run. How much of the other isotopes of hydrogen are
Max?
deuterons and protons?
Yeah, I know. That's a good question.
I know you know. I just don't have any idea because, I mean, in the extreme, there's a hell of a lot of protons around, and they would compete for the sites with your tritium, but maybe there isn't very much.
So I think it goes back to the fact that we need a full isotopic analysis evolution of the salt. So we need to know all of the hydrogen, all of the oxygen, all of the nitrogen, so that we can understand that. I completely agree. It's a gap. I don't know why we haven't been counting them before.
But there is not a source. There is
You
not a
don't-
source.
Okay.
Like here, there is a source of tritium, that is lithium-6.
Well, the
and lithium-7.
deuterons have to be nuclear, but the hydrogen, the protons can come from anywhere. I mean, it's just plain old, the world is full of it,
Yeah.
right?
NP too. You have NP reactions in the metal.
Yeah, no, I mean, of course, I mean, every time you make an NP, you get out.
It's thermoreactor, so you won't have many NP.
No, so I don't know the answer to that, and it occurred to me that you ought to think about you put out those diagrams with all those NNAs and stuff, NN alphas and stuff. There may be some NP reactions that produce a lot of hydrogen that's going to get in your way.
Yeah. So it'd be great to work with Max on that.
And
so
I
that we
wouldn't-
can figure it out.
And I would not suspect that there's very much deuterium,
Okay.
because the ND reactions, I mean, they're just rare compared to NP reactions, I would think.
Yeah.
Actually, a question. So you showed a lithium concentration distribution within the graphite.
Yes.
The somehow is similar, or the trend is similar to what you see in tritium. So could it be that tritium stays where it's produced rather than diffusion?
Yes.
Could be. Yeah. I don't know. I don't know if the numbers would match up.
And yeah, I don't know if they would match up, but the distribution is clear.
Yeah,
I mean,
sure.
it's similar.
Could be, yeah.
Further questions? Good. Not right on time for the faculty grad student. Social?